Welcome back. We're going to be continuing on with the 2013 grade 9-10 Canadian Intermediate Mathematics competition. That's what we're doing today. So let's take a look. We left off question number 1. Now we're into question number 2. That's the part B question, so let's take a look at it. So we'll need a written solution here. In each part of this problem, cups are arranged in a circle and numbered 1, 2, 3, and so on. So here we have a nice little picture. I guess they go up to 12 here. A ball is placed in cup 1, and then moving clockwise around the circle, a ball is placed in every nth cup. Okay. The process ends when cup 1 contains 2 balls. For example, starting with 12 cups and placing a ball in every third cup, balls are placed in order in cups 1, 3, 7, 10, and 1. 1, 1, 2, 3. Cup. Drop a ball in, 1, 2, 3, drop a ball in, 1, 2, 3, drop a ball in, and 1, 2, 3, we get back to 1 and the process stops. Alright. There are 12 cups in the circle, that's question A, or part A. There are 12 cups in the circle and a ball is placed in every 5th cup, beginning and ending with cup 1. List in order the cups in which the balls are placed. So this looks like it's going to be sort of modular arithmetic. So it's something that people are occasionally familiar with. It's like counting on a clock. There is no 13 o'clock. Once you get over 13, or once you get over 12, you subtract 12 to get back down to a regular hour number. Same sort of thing. I suspect that's why they have the 12 here, like 12 cups here, so you can sort of make the connection of, oh, it's clock, because there's 12 at the top and everything like that. So we'll be counting using modular arithmetic, so there'll be no numbers sort of higher than 12 is the idea. If we wanted to be pedantic, we could, in our minds, change cup 12 to cup 0. Not really that important. So, list in order the cups in which the balls are placed, and we're going every 5th cup. All right. So, 12, 1, 2, 3, should be a 9 over here, and then a 6 down here. Just working out the clock. 4, 5, 6, 7, 8, 9, 10, 11. It kind of looks like a diamond. It's not quite a circle or anything like that. Alright, so let's get it out a different color. We don't usually use orange. Alright, so a ball goes into cup 1. And then we go 1, 2, 3, 4, 5, and we deposit a ball. So we have 1, then we go to 6, then 1, 2, 3, 4, 5, and that a cup goes into 11, or a ball goes into cup 11. Then we go 1, 2, 2, 3, 4, 1, 2, 3, 4, 5. We just do it this way. So that's 4, and then 1, 2, 3, 4, 5, up to 9. We can just get a little faster as we get more comfortable with this. If you need to, keep drawing, but as you can see, my drawing is starting to get a little messy. Probably once I hit the 12, I might have changed color. So from 9, we go 10, 11, 12, 1, 2. Then 2, we should go all the way up to 7. Then we go to 12. Then 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. We're up to 10 now. 1, 2, 3, 4, 5. We're down to 3. Then that'll go to 8. And then from 8, we go 1, 2, 3, 4, 5. All the way back to 1. So I believe the question said we stop at 1. List in order the cups in which the balls are placed. So it's beginning and ending with cup 1. Alright, so we actually turned out we put a cup in every single ball. But we wanted in order exactly what we're doing. So we'll just explain 1, 6, 11. I mean, there's probably maybe 1 mark for this whole thing, maybe 2, just because it's a long sequence. So there wasn't a whole lot to that one, but I mean, that's just part A. We have B, C, and D to do. Okay, so B part. There are 9 cups in the circle, and a ball is placed in every 6th cup, beginning and ending with cup 1. All right. List the numbers of the cups that do not receive a ball. All right. So automatically, being experienced with modular arithmetic and this sort of stuff, I can see there will be some that don't receive a ball just because 6 and 9 have a common factor of 3. So if you were into ring theory, which you shouldn't be with grade 9 and 10, but just advertising university level math, you would know that 6 is a 0 divisor in Z9. Someday you'll know what that means. But let's take a look at it. 9 is small enough, we can just draw this out. Okay. We can put 1, 2, I'm not spacing this right, 3, 4, 5, 6, 7, 8, 9. It doesn't actually matter the spacing. So starting with cup 1, we go until we hit cup 1 again. Green, we don't usually do green. Okay, so a ball goes into 1. Then we go 1, 2, 3, 4, 5, 6. The ball goes into 7. So we go 1, 7. Then we go 1, 2, 3, 4, 5, 6. So a ball goes into cup number 4. Then we go 1, 2, 3, 4, 5, 6, and a ball goes back into cup 1. So these are the ones that get balls. I think we were asked which ones don't get balls. So 2, 4, 5, 6, 8, and 9. Yeah. So check here. List the numbers of the cups that do not receive a ball. Okay, exactly what we were asked to do. C part. There are 120 cups in the circle. Okay, I can't draw that one. And a ball is placed in every 3rd cup, beginning and ending with cup number 1. How many cups do not contain at least 1 ball when the process is complete? Explain how you obtain your answer. It's kind of weird that they say explain how you obtain your answer, since you're supposed to be sort of at least trying to explain things every single time. But we've mostly been doing proof by picture, so maybe that's why they included that. Maybe they don't want people trying 120 cups. All right, so 120 cups, balls placed every 3rd cup. Okay, so the real question is, how far do we get to go to cup number 1? Okay, so we've seen with 12 cups, going every 5th one, we hit every single cup. And it took 12 steps to get back to 1. And the reason for that is, what's the best way to explain it? The smallest multiple of 12 that is also a multiple of 5 happens to be 5 times 12 is sort of the reason there. 9 cups and every 6th cup, beginning and ending with 1. So how many cups did it take to get to 1? It took 3 because 3 times 6 is the smallest multiple of 6 and 9. Alright, so we can sort of try and put that into practice here. So how many balls does it take to get back to 1? So after putting a ball in cup number 1, how many more do we need until the second one goes into 1? You can try and see or convince yourself, or maybe you can come up with your own proof. If any cup gets a second ball before 1, then that means that the cup before it also has just gotten its second ball, and so on and so on. It's just, with sequences like this, one gets the first ball, and then the next time after 3, 4 gets its first ball, and 7 gets its first ball. Suppose that 2 got its second ball, and we haven't hit 1 yet. Then working backwards, what number did you just come from? You just came from 119. So did 119 just get its first ball, or did it get its second ball? Well, if it just got its first ball, how did we get to 2 and give 2 its ball? That's the level of thinking here. So if we can figure out how many cups it takes to get back to 1, since 1 is the first cup to get a second ball, we'll then be able to say, well, every cup in between got its first ball, and so we'll know how many cups got balls, and then we'll be able to say how many cups did not get balls. So n times, what do we have, 3. So that's the smallest multiple of 3 and 120, because 120 is how many cups you have. You can generalize this into a general theory. So if you are skipping every k many cups, and you have m many cups in total, then n is the number of steps, where n times k is the smallest multiple of both k and m. It's a general theory we can make. So why don't we actually write that? So it's a nice little bit of theory that we can add here. And we could prove this with modular arithmetic, or if we needed to, ring theory. The question doesn't really call for it, and we haven't had a whole lot of experimentation to justify the theory. So we're just trying to explain our answer here. And since the lowest common multiple of 3 and 120 is 120. It's not 3. It's 120. Greatest common divisor of them is 100. Is 3. Right? You might have been able to just say this right off the bat. We can see every third cup we're going around 120 times, so everything's going to work out perfectly. And we just do 40 steps, and then we'll be back to 1. We're counting the cups that are equivalent to 1 modulo 3 is another way to look at this. So 40 cups will get balls, including cup number 1. We can either count them at the start or count them at the end, depending on how we count our steps out. So we were asked how many cups will not have a ball by the time we get back to number 1. Well, every third cup is getting a ball, and it takes 40 cups to make it all the way around, because 120 divisible by 3. So 40 cups get balls, so that means 80, which is the remaining cups, will not have balls. Okay, and we explained it a little bit. We stated a general theory that could be potentially proven if we needed to. But, it was a fairly basic explanation. I find with these contests, you have to look at how many parts there are in order to gauge how much justification you really need to give. If you're looking at a question with 4 or 5 parts, each question, I think, if we scroll up to the very top of the contest, so part A is worth 5 marks, part B is worth 10 marks. So you don't need to be the most rigorous person in part A. And with part B, if you've got something worth 5 marks, then odds are at any given step you're looking at 2 or 3 marks for that particular part. And you have to figure, well, what are they giving marks for? It's a petty thing to just be thinking in terms of marks and not in terms of math. But sometimes when it's crunch time on a contest, you have to gauge and balance your rigor with what the question's likely worth. All right, so D part. There are 1,000 cups in the circle, and I definitely can't draw that one either. And a ball is placed in every 7th cup, beginning and ending with cup number 1. Determine the number of the cup into which the 338th ball is placed. Okay. So every 7 cups, so we go 1, then we go 8, then we go 15, and so on. And we want 338th cup. So sure, we're going from 1 to 8. We're just talking about 2 cups there, 1 and 8, but we're actually covering 7 cups, 2, 3, 4, 5, 6, 7, and 8, in order to get from 1 to 8. That's how we determine our position. So we pass over 7 times 338, which is 2,366. That's how many cups we pass over. So if we were just counting along in a giant circle, we'd be then, after 1,000 cups, we'd move to cup number 1001. So we can go around the circle once by we're not dumping a ball into every each of these 1,000 cups. But the point is, as we are putting balls in cups, we are counting along, and we count out 2,366 cups. Well, after our 1,000th cup, we should be at cup 1,001, but it doesn't exist, so we would go cup 1, and then we count again and again. So at 2001, at cup number 2001, that we're back to 1 again. So we go around the circle twice, and we're back at cup 1. So what we can do is every 1,000 we can basically restart our count. We're counting along. Okay, we're at 1, and then we go to cup. We count cup 2, cup 3, cup 4, cup 5, cup 6, cup 7, cup 8. We put a ball there. Then we count cup 9, count cup 10, and so on. So we're counting along the cups, and occasionally we're putting balls in things. So cup 1 plus, so the 366th cup after 1 is going to be cup 1 plus 366. So the 338th ball is going to be put in cup 367. And we can use our previous theory to see what number ball that is. I'm pretty sure, however, that since 7 is relatively prime to 1,000, this will be the first ball put in cup 367. So that's sort of an interesting question. It's got 4 parts, so not a whole lot of explanation needs to be given to any one part. It's got some modular arithmetic in there, which is a great springboard to studying ring theory in university. Ring theory, excellent theory, very robust, very expansive. But, I mean, that's all for another day. This is a grade 9-10 competition, so we should never get too bogged down in what lies beyond. If you don't want to go to university and study math, that is fine. But this stuff is out there, and sometimes when you do these contests, you get sort of a glimpse of something that lies beyond. And, a couple of you might be enticed to study that. But, keeping our eye on the prize, that was question number 2. 4 good parts, interesting little modular arithmetic, counting sort of arguments. And, yeah, not a lot else to say. We can move on to question number 3. But we'll have to do that in the next video, so won't you join me please then?